So this is section 4-1, part 2. We'll call it like B. And this is all about linear and angular speed. Okay? And it's speed, not velocity, because the difference, who knows the difference between speed and velocity? Anyone know the difference? Yes?
Velocity has an initial speed, final speed.
Not quite. We're gonna sorry, Sam.
Is velocity speed in a given direction?
Yeah, velocity has a given direction. It can have a negative or positive side attached to it, whereas speed is just that's the value of velocity, right? So if you're going backwards, then you're going to have negative velocity. If you're falling down, you might have negative velocity, and so on. Okay, so we're going to talk about this as it relates to circles. Okay, so linear speed is, well, first let's talk about angular speed. Angular speed is just given by the equation theta divided by t, and where theta is usually in radians. Okay, so if they say I'm doing 2 pi radians per second, you could have that in you could have that in degrees too, okay? But usually when they're talking in this book, they're going to be talking about radians. So you could do 2 pi radians per 5 seconds or something like that, or 2 pi radians per second, okay? So I'm going to do an example problem in a second, okay? Then we have linear speed. Linear, that's not very good writing, is it? Linear speed, and that's equal to s divided by t. And s is the arc length. That's not very good A, is it? Okay. S is called the arc length. Okay. And S, if you remember, anyone remember what the formula for arc length is? Go ahead, Connor. No, not Connor, sorry, Colton. That is right. First it's just r theta, okay? Where theta is measured in radians, okay? So you could find, so before when you took geometry, S was equal to n over 360 times 2 pi r. Do you remember that? Okay, n over 360. But when you have radians, you can just use this simple formula, r times theta. So for, and you should know this formula too, because this comes up in your homework a lot. So S equals r theta. That means that theta is equal to S divided by R. This was kind of your definition of what a radian is. So if S is 2 pi, and I have a radius of 1, then you're going to have a theta of 2 pi. Okay, meaning your angle is 2 pi all the way around. Okay, well, we'll talk. I think I have an example in a second. So theta is equal to S over R, and this one you might use less, but in your homework for, I think it's numbers 89 through 100 or something like that, you're going to be asked to solve for one of these 3 variables given to the other ones, and you could interchange this and rewrite this as R is equal to S divided by theta. So S equals R times theta. Theta is equal to S over R. R is equal to S over theta. And I think that's all the combinations of that you could have. The R, S. So for example, let's just do a little, it's before I get into the linear speed problem, let's just find the arc length of a central angle. Can you see that? Am I too far down on the screen? I'll move it up in a second. Find the arc length of a central angle that measures 60 degrees with a radius of 5 inches or something like that. So that's the arc length on a circle, I guess I should have said, of a central angle that measures 60 degrees with a radius of 5. And it's good to kind of draw pictures of things, not of anything, but of circles. So let's see if I can find my circle drawing tool. There it is. Right? So I'm going to draw a circle. Isn't that cool? And I'm going to draw in this angle right here. And this is 60 degrees. And this is 5. Okay? And basically what you're trying to find when you're finding that, you're trying to find how far is it from here to here. So I could use this formula, but what's wrong with that formula? What's wrong with this 60 degrees? What do I have to do with it? Convert it into radians. How many radians is 60 degrees? Pi over 3. Okay? And so all you have to do is plug into this formula. So S is equal to pi over, or 5 times pi over 3, right? So it's just 5 times pi over 3, which comes out to be, I don't know, who's got a calculator? Someone got a calculator? I should have done this beforehand. What did you get there, Alex?
So 5.2.
So that's about 5.2. Now, before, when you took geometry, we had a formula that looked like this. L equals n over 360 times 2 pi r. You don't have to know this one, but I'm just showing you that it would give you the same result, okay? So if I plugged in 5 in here, okay, and I plugged in 60 degrees in here, do you remember doing this in geometry? Vaguely? You don't remember doing that? That's because you didn't have me as your teacher, but you would have, but some of you did. Like 60, 3/60ths is the same as 1/6 times 2 times pi times 5, and, right? Because 60, 3/60ths is 1/6, and that would give you 10 pi over 6, 10 pi over 6, which is equal to 5 pi over 3, which is exactly the same. See? 5 pi over 3, 5 pi over 3. You remember that formula? No one remembers that formula from geometry? N over 360 times 2 pi r? Yes, you do. Come on. Okay. So anyway, just when you're using any one of these formulas, just remember that you have to be in radians. You can't be in degrees, otherwise you're going to get the wrong answer. Even if they give you the question in degrees, you got to be in radians. All right. So now we're going to use arc length to solve a problem. And let me see, we're going to, not arc length, yeah, arc length, but we're going to solve an angular velocity problem. If I can find it, arc length problem. There we go. Arc length problem, arc length problem. There we go. I made this one up, but it's very similar to ones that you might see in a book. Not that one, we're going to do this one first. But let me take a picture of it and place the capture in a new page. Linear and angular speed. So back when I was a kid, I grew up next to this, it's a true story, I grew up next to this amusement park in New York. It was called Playland. It was in the movie Big, where they walk on the boardwalk. Did you ever see that movie? That's an old one. And that was my hometown. It was kind of on Long Island Sound, about 20 miles north from New York City. And there was a amusement park right down, like if you cut through the woods, you could get down to the parking lot in this amusement park. My friend Jimmy and I used to go, and we would mooch tickets for all the rides. And the way we'd mooch ticket, even though we weren't like poor kids, we'd like dress up in raggedy clothes. And I grew up, here's my picture. I grew up, so here's New York State, and sticking out here is Long Island. And I kind of grew up here. This is Long Island Sound in there, like Cape Cod and all that stuff, Massachusetts up there. And I grew up right on Long Island Sound, which is kind of cool. But these high school kids, when I was a little kid, not in high school yet, Jimmy and I, who's now an eye surgeon, okay, we used to dress up in raggedy clothes, and these kids used to take the ferry boat over from Long Island and go on all the rides, and they'd get books of tickets. And we'd dress up as they were leaving and go, hey, do you guys have any extra tickets you don't want? And we get all their tickets to go on the rides. It's not like villages where you pay a fee and you go in and you have to pay tickets for each ride. So we get to go on all the rides, and the guys got really sick of us and would put us, like one time he stuck me on the upside down Ferris wheel upside down and wouldn't let me out because we were going on the ride so many times, you know. So anyway, there's this one ride called the, I think it was called the Kentucky Derby. And it was like a merry-go-round, but it went really, really fast, okay? So it wasn't like your normal merry-go-round. It was like a merry-go-round. If you didn't hang on, you'd go flying off the edge, right? And so with the merry-go-rounds, so this is, Fred is on a merry-go-round, which is making 1 revolution in 4 seconds. If he stands on the outside of the merry-go-round, which has a 20-foot radius, which was probably more than 20 feet, okay? And I tried to make this as realistic as possible. What is his linear speed in feet per second, and then in miles per hour? If Fred moves closer, so that he was 10 feet from the center, how would his angular speed change? How would his linear speed change? Okay? So the way you would do that, okay, you're going to, first thing, what is his linear speed in, what is his angular speed, okay? So the first thing, angular speed is, I think, I'm not sure in this book what symbol they use, but a lot of times for angular speed they use like omega, which is like, that's not a very good omega, but kind of a curvy W, okay? And it's just equal to theta divided by t, okay? And so if he stands on the outside of the merry-go-round and has a 20-foot radius, what is his angular speed? Well, if he's going around 1 revolution in 4 seconds, how many degrees or how many radians is 1 revolution? 2 pi radians, right? 1 revolution is 2 pi. So his angular speed is 2 pi radians per 4 seconds, or it's equal to pi over 4, and I guess that's radians per pi over 2. Okay, pi over 2 radians, pi over 2 radians per second. Okay? If he moves closer, is his angular speed going to change? Okay? Is he still rotating the same amount of revolutions per second? Right? So if he's standing on the outside and the horse is on the outside too, it's not going to take him more time to go around if he's on the outside as he's on the inside. But who's going faster, the guy on the outside or the guy on the inside? It's the guy on the outside. So angular speed, it doesn't change, right? The angular speed, it's always rotating at a certain rate. But if you go on the outside, then it's going to change. So to find the linear speed, okay, he's got a 20-foot radius. So the linear speed, which we'll just call, what do we call it? Let's call it linear speed. Ls is equal to S divided by T, which is, and this is the arc length, remember? Arc length. So how do I find the arc length in this case? How far is he going? 2 pi, so arc length is S, that's our theta, right? And so R is what? 20, and theta is 2 pi, and T is 4, right? So that's, he's going, and that's in feet. You have to put the units. That's, he's going, well, I could divide that by that, right? 20 divided by 4 is 5. And that's right? 5 times 2 is 10. So he's going 10 pi feet per second. I don't know if that's that fast, but that's about 31.4 feet per second, right? Yes, ma'am.
Do you want us to reduce our,
Fractions?
or reduce the pi down to,
Well, in this type of problem, it's kind of nice to know, like, in miles per hour. Because the next thing they ask is, what is his linear speed in feet per second? In miles per hour. Well, this is a little, what do they call that? Dimensional analysis or something like that? 31.4 feet per second times how many feet in a mile? 5,280 feet is equal to 1 mile, right? And then you got to turn seconds into hours. How many seconds in an hour? 3,600, right? Because there's 60 times 60. So there's 3,600 seconds in 1 hour. Have you guys done this before in science? Okay. So then you cancel out the feet with the feet, the seconds with the seconds. And if you do that, I did this, I think you get, I think I did this correctly. I think you get 21.4 miles an hour, okay? So that's pretty fast for being on a merry-go-round. And when seriously, it was really, like the guy, when you were on the ride, he would take your tickets, and he would be like, it was really cool, because he'd be like leaning in, you know, taking your tickets like that. I go, oh, that was like a fun job, and he'd be walking around like this. And then when he went to the inside, he didn't have to lean as much, because how fast is he going when he's on the inside? Yeah, all you'd have to do really, right? If he's on the inside, this just changes to 10, right? So it's just going to get cut in half. You get that? So you don't have to do all the math again, right? Because the radius is half, and it's a linear relationship. It's not squared or anything. So when he's on the inside, he's only going to be going, what's that, 10.7 miles per hour when he's on the inside. Okay? So he's going a lot slower. So we'd always try to go on the outside because that was the most fun because you're going as fast. Because at one time my brother came with me and I pushed him anyway. So it's pretty, that was pretty fun. Okay, so that's one type of word problem that you're going to see. The rest of the math is easy. And the second type of word problem that you're going to see, and everyone goes, how do you do this problem? I don't understand what they're talking about. It's really simple. You just have to understand what they're talking about. Here's another arc length problem. And so in this one, you have, if the Earth is assumed to be a sphere of 6,378 kilometers, what is the difference in latitude between Syracuse, New York, and Annapolis, Maryland, where Syracuse is 450 kilometers due north? Okay? So what you have to do is pretend that this is the Earth. Okay? So here is the Earth, right here. Okay? And on the Earth, you have, I don't want arrows on the end, okay? On the Earth, you have, what's this? Syracuse, New York, and Annapolis, Maryland. They're above the equator, right? So so this is kind of an exaggerated picture of it. And they say that this radius is 6,378. Yeah? And then where Syracuse is 450 kilometers due north of Annapolis. So where am I going to put that? That's the arc length. So even though you say, well, that's not 450 kilometers, because you're kind of thinking in 3 dimensions, right? So if it's due north, like if I drew this in 3 dimensions, this would be due north on the sphere of the Earth if I took like a cross section of it. You understand what I'm saying? So really, it's like called the great circle. So if I slice the Earth down the middle, this would be the arc length of a circle. So really, all you're trying to do is find this angle right there, and then you have to figure out how many degrees they are apart. So remember this formula, S equals R theta. You could either plug in S and R and solve for theta, or you could rewrite this as theta is equal to S divided by R. Okay? And when you do that, what's S in this case? 450, right? And R is 6378. And then you plug that into your calculator, and you get that theta is about equal to 0.07055 radians. Okay? But latitudes are usually in degrees, right? So what is the difference in latitudes? So latitudes are usually in degrees, so how do I figure out how far that is in degrees? Multiply by 180 over pi. Because this is radians, right? Even though there's no pi in there, it's still radians, and I'm going to use the conversion factor where I'm going to multiply by 180 divided by pi. Okay? And when I do that, I get that is approximately equal to 4.04, I think. I think my math is right. 4.04 degrees. So that's a difference. And when you're doing these types of word problems, try to make sure your answers make sense. Most of the time they make problems that make sense. So if you got, on the last problem, if you said that Fred was going 250 miles per hour, probably did something wrong, okay? Because most of the time, the books and we try to make answers that make sense. If you found that Annapolis, Maryland, and New York, Syracuse, New York, are 500 degrees in latitude, well, there's only 360 degrees difference, right? So 4 degrees sounds about right, you know? So I would kind of make sure your answers make sense. And unfortunately, that's all I have for you today. Okay, so the homework is relatively short, I think, and you can get started on it and do it right now. And I'll walk around and check your other stuff and try to pass back homework from you. And that's that. Should I just walk around and check, or should I collect it? Walk around and check. You may go to the bathroom. Whoops, wrong thing. Stop. I have to